First, you have to know what is a limiting reactant in a chemical reaction, right? I mean, isn't it just reactants, the things you mix together, products, the things that come out? So what is a limiting reactant? All right, take chemistry, put it out of your mind, and think instead about making sandwiches. You can think about peanut butter and jelly sandwiches, or if you want, you can think about ham and cheese sandwiches. I don't care. I'm going to talk about peanut butter and jelly sandwiches. So I don't have a quantitative number, but I know roughly 1 spoonful of peanut butter goes on 1 piece of bread, and a spoonful of jelly goes on the other piece of bread. That's going to form 1 sandwich. 1 spoonful of peanut butter, 1 spoonful of jelly. All right, so if I have a full container of peanut butter and a full container of jelly with the same roughly volume of each, then I'm going to be able to make a lot of sandwiches, right? But what if I have a full jar of peanut butter and just a tiny amount of jelly? Or flip it around. What if I have a tiny bit of peanut butter, just a little bit in the bottom, but then a full jar of jelly? Well, what's going to happen is I'm going to run out of one of the reactants first. And here's the thing. With sandwiches like PB&J and also in chemistry, once you run out of one of the ingredients on the left-hand side of the reaction, the reactants, once you deplete one of them, the reaction stops. It can't go any further because once you've depleted one of those items, then you just can't make any more. For instance, sodium chloride. Sodium and chlorine, 1-to-1 relationship, right? If you run out of sodium, then you can't make any more sodium chloride. So the sodium is the limiting reactant. So a limiting reactant is the reactant that you run out of first. I'll say that again. The limiting reactant is the one that you run out of first. And when you run out of one of them, it is the reactant that basically terminates the reaction because it can't go anymore. So I know it seems silly for me to write this down, but I'm going to write it down because it's a visual way of understanding this. Let's say I'm making these peanut butter and jelly sandwiches, right? I have a whole lot of peanut butter. And I'm going to add to that jelly, which is in its own separate container. However, I only have a little bit of jelly, all right? So what's going to happen in this situation? Well, I can certainly make some sandwiches. I mean, I can scoop and make a sandwich and scoop and make a sandwich, but I'm going to deplete the jelly first. And when the jelly is gone, even though I have a bunch of peanut butter left, I can't make any more sandwiches because I need both of these things to make a functional peanut butter and jelly sandwich. So in this case, we say that the jelly is what we call the limiting reactant. The word reactant just means the stuff on the left-hand side of the reaction. The limiting one is the one that basically runs out first and it limits the reaction. All right. Now, even though it's a little silly, we're going to do the same thing again. We're going to draw another tub of peanut butter and another tub of jelly, and we're going to give ourselves a lot more, peanut butter. Well, not as much as this, but we still have a lot of peanut butter. But we're going to give ourselves a lot more jelly, right? Now, in this case, the amount of peanut butter and jelly, the difference is not so extreme. But I think you can still visualize what's basically going to happen. I'm going to take the peanut butter and jelly out, make a sandwich, another one, another one, another one. Eventually, I'm going to run out of the peanut butter first, right? I'm still will have some jelly left over, maybe this much. But it doesn't matter because once I run out of peanut butter, I can't do anything anymore. Peanut butter, in that case, is the limiting reactant. So we say that the peanut butter limiting reactant. Now, in chemistry, we care about figuring out what the limiting reactant is because it's going to determine how much product we make. If we're trying to make, for instance, sodium chloride, 1 sodium atom for every chlorine atom, then how many of those formula units of sodium chloride can we make? It's going to be determined by whichever one of those runs out first. Whenever you identify what the limiting reactant is, which one will be depleted first, that is what is used to then calculate how much product you make. Because the other reactant will be what we call the excess reactant. At the end of the reaction, we're going to have excess reactant left over. In other words, in this situation, the limiting reactant was the jelly, but the peanut butter was the excess reactant. In other words, once we finish making sandwiches, we're going to have peanut butter left over. Here, the peanut butter was the limiting reactant. The jelly was the excess reactant. After we deplete them to the point where the peanut butter goes to 0, we're done making sandwiches, we'll still have some jelly left over. So if you have a limiting reactant, and you almost always will have a limiting reactant in a real chemical reaction, once you determine that, that is what you use to calculate how much product you have because the reaction stops once the limiting reactant is depleted. And then you may have excess of the other reactant left over that's just sitting in the vessel. It's not reactant. It's not reacted with anything, but it's still there. That's called the excess reactant. All right, so peanut butter and jelly is fun, and I think it's a great way to introduce this. But before we solve our first real problem, because I do have a real problem here, I want to talk about a simple chemical reaction and do some simple calculations. Not really a full-blown problem, but a really good introductory problem here. Let's talk about water. And we know to make water, the reaction is 2H2, which is a gas, and we react that with O2, which is a gas, and that's going to produce 2H2O, which, depending on the temperature and such, it's usually going to be a gas that forms there as well. But it could theoretically be a liquid if it's cooled down immediately. All right, now what does this reaction mean? These coefficients are the mole coefficients, right? So this means 2 moles of the hydrogen H2 molecule combines with exactly 1 mole of the oxygen O2 molecule. And these are exact numbers. It's a 2-to-1 ratio of moles, okay? And when that happens, I form exactly 2 moles of the water molecule. Now, this means the following. Here's where we start to get a little bit more quantitative than the peanut butter and jelly example. If I ask you, if I, in a vessel, mix 2 moles of hydrogen with 1 mole of oxygen and then react it, how much product will I form? Well, I've already given you the numbers exactly as they're written on the board, and you know that if 2 moles of hydrogen react with 1 mole of oxygen, it's going to produce exactly 2 moles of water. So in that case, if I really do have exactly 2 moles of H2 and 1 mole of O2, then every single molecule will then have been reacted to combine together to form these water molecules, and we'll have 2 moles of these water molecules floating around. But since I reacted exactly 2 moles with 1 mole, there's nothing left over because they've all combined into these molecules, and there's nothing left over. There's no real limiting reactant there, and there's no real excess reactant because everything was utilized, okay? Now let's take another example. Let's say, I'll just put say, ... Let's say that the following situation happens. Let's say I react 2 moles of H2. I react that with 1,000 moles of O2. What is going to happen? Now, it was very easy when I told you that it was just 2 moles of hydrogen and 1 mole of oxygen because you know they combine and you know that's what's going to happen. But what happens if I actually have a vessel and I put 2 moles of hydrogen and I mix 1,000 moles of oxygen in there and then I react it? What's going to happen? Well, of course, the molecules of hydrogen will begin combining with the oxygen. Of course, that's going to happen. But according to the reaction, for every 2 moles of hydrogen, it only really reacts with 1 mole of oxygen. After that, the hydrogen is depleted. I have excess oxygen in this vessel. I have excess oxygen. So, of course, it's going to fully deplete all of the hydrogen, and it's going to make my 2 moles of water. I'm going to get 2 moles of H2O out of it. I'm going to react and get 2 moles of H2O out of it. What's going to actually happen is the 2 moles are going to go ahead and combine with 1 mole of oxygen because that's what the reaction says, but I have 1,000 moles of oxygen. So what actually happens is I have 999 moles of O2 left over. This is called, the O2 in this is called the excess reactant. And the hydrogen is called the limiting reactant. Why is it the limiting reactant? Because the limiting reactant, the definition of it is it's the reactant present on the left-hand side of the chemical reaction that runs out first. And when it runs out, the reaction stops. So because it's nothing to do with well, it is have to do with the numbers, but the reason that it's the limiting reactant is because you know that it reacts 2 to 1, right? 2 to 1 mole. And there's so much oxygen there that, of course, it's going to connect and bond with 1 mole of oxygen, but then the reaction is going to stop. How much water will it produce? You know that 2 to 1 produces 2 moles of water. That's why we could write that down. Once it's depleted, though, it only soaked up and used 1 mole of oxygen, so there was 999 moles of oxygen left over, and that's why it was the excess reactant. The limiting reactant was whatever was utilized first. Depleted, the reaction then terminates because there's nothing left to react. We have all this O2 left over, but there's no more hydrogen, so nothing else happens. It just sits there. All right, now let's go the other way. And let's say that actually I take 1,000 moles of hydrogen, right? And I'm going to react it with 1 mole of oxygen. So this is the reverse situation, right? What's going to happen? Ton of excess hydrogen, lots of excess hydrogen. It bonds in a mole ratio of 2 to 1. Now I told you that 1 mole of oxygen was present. So that is going to connect with 2 moles of the hydrogen. And so, but once the oxygen is depleted, the only mole I had there, it's going to bond just the same. And I'm going to get out of it 2 moles of H2O, just like before, because 1 mole of oxygen was I had enough excess of the other reactant to fully bond with all of the puny tiny amount of oxygen I had. And since I know that for every 1 mole of oxygen, if I have enough hydrogen there, it's only going to make 2 moles of water, I can write that down. But in that situation, I know that I'm going to have 998 moles of hydrogen left over. How is that? Because 1 mole is going to bond with 2 moles of hydrogen according to the reaction, but I have 1,000 moles of hydrogen, so there has to be 998 left unreacted, and this is called the excess reactant. And in this case, the O2 is the limiting reactant. Okay, so you see how it's the same definition plays no matter which way you go. I gave you a reaction, a very common one that we should know in our mind, water. And we say that if we have 2 moles of hydrogen and 1 mole of oxygen, then everything is depleted. There's no real limiting reactant. Everything is used up, and we have 2 moles of water. If I give you a ton of excess hydrogen, then the oxygen's the limiting reactant. But if I give you the other way, a ton of the other reactant, then the other reactant is the limiting there. So if I gave you a lot of excess oxygen, then the hydrogen was the limiting reactant. If I gave you a lot of excess hydrogen, that was the excess reactant, and the oxygen in that case would be the limiting reactant. Now let me give you another situation, which is, I think I'm going to do it on the other board. Another situation that is much more like a chemistry problem. Let's say that instead of these extreme situations, let's say that I react 10 moles of hydrogen with 7 moles of oxygen. Which one of these is the limiting reactant? And how much water will be made? You see, now it's not so easy. This is how chemistry problems can start to build. Everything before is very easy to understand. Why? Because the coefficients were easy and I gave you very easy numbers to compare. But now it's not so easy because it's 10 moles of hydrogen reacting with 7 moles of oxygen. Which one is going to run out first? That will be the limiting reactant, and we can use that to predict how much how much product we're going to make. Well, here's how you tackle it. If you're given 2 different amounts, in this case moles of hydrogen and oxygen, what you do is you say, okay, if I react 10 moles of hydrogen, according to the chemical reaction, how much oxygen will it require to fully react with that 10 moles? And then we'll do the same thing the other way, and we'll see which one is really limiting and choking the reaction and preventing it from continuing. How do we do that? Well, let's take the first thing. Let's say 10 moles of hydrogen. Now let's calculate how much oxygen, according to this chemical reaction, is going to be needed. We know that they react in the ratio of 2 moles of hydrogen to 1 mole of oxygen. So for every 2 moles of hydrogen, it reacts with 1 mole of oxygen. Now I arranged it this way to cancel. What you're calculating here, when you divide by 2, is you're calculating how many moles of oxygen will be required, according to that reaction, to bond and fully react with 10 moles of hydrogen. So 10 divided by 2 is 5 moles of O2 required. All right, now I'm telling you that 5 moles of oxygen are required, but I'm in this case reacting the 10 moles of the hydrogen with 7 moles of oxygen. So I only need 5 moles of oxygen to actually react with it, but I have 7 moles. In other words, I have an excess amount of oxygen. Oxygen cannot be the limiting reactant because I have more than I need to bond and react with the hydrogen present in that vessel. So, because I need 5 moles of oxygen, but I actually have more than that in the vessel, then what we basically say is that the in this case, the oxygen is the limiting, I'm sorry, not the limiting, the excess reactant. And if this is the excess reactant, then hydrogen is the limiting reactant. Right? Because limiting reactant, again, all it means is that which of these two reactants is going to run out first. And because it requires 5 moles of oxygen to react with 10 moles of hydrogen, then as soon as the 5 moles of oxygen is used up, and then I've definitely used up all the hydrogen there, and that's going to run out before the oxygen's going to run out, so the hydrogen has to be the limiting reactant. Now, we've determined the answer to this. We figured out which one is the limiting reactant just by using this, but we can use the other piece of information too. You can calculate it multiple ways. Let's start with 7 moles of oxygen. Let's start with that instead of with the hydrogen. How many moles of hydrogen will be needed to react with that? 1 mole of oxygen for every 2 moles of hydrogen. 1 mole of oxygen for every 2 moles of hydrogen. Cancel, cancel. What we're calculating here is, if you start in a vessel with 7 moles of oxygen, how much hydrogen do you actually need to react with it to fully react with it? 7 times 2, 14 moles of hydrogen required. However, 14 moles of hydrogen is required, but in the vessel I only had 10 moles. So this tells you right away that it actually requires more hydrogen to react with this oxygen than is there. That means I'm going to run out of hydrogen first. And so the same exact logic is telling you that you've basically figured out here that hydrogen is the limiting reactant. I'm going to put LR for limiting reactant. And the oxygen is the excess reactant. This is limiting reactant, excess reactant. It's the same exact conclusion that we drew above. Whatever reactant you start with, if you calculate how much of the other reactant you need, then you can deduce which one is the excess and the limiting reactant. No matter which reactant you start with, you're going to get to the same conclusion. All right? Now, the natural question that you always ask in chemistry is, once you know what the limiting reactant is, how much product will form? In this case, the product is water. So if I just told you, hey, 10 moles of hydrogen is mixed with 7 moles of oxygen in a reaction vessel, how much water will form? Well, first thing you have to know is which one's going to run out first. We just figured that out. How do we figure out how much water is going to form? We know from both of these different methods, we figured out that hydrogen is the limiting reactant. That means hydrogen is going to run out first. So I'm going to start out with the 10 moles of hydrogen. What you do is you use your limiting reactant to calculate the product, because you now know that the limiting reactant will run out first. 2 moles of hydrogen produces 2 moles of water. 2 moles of hydrogen produces 2 moles of water, according to that reaction. Cancel, cancel. So what you figured out is these 10 times 2 is 20, 20 divided by 2 is 10, or you can cancel the 2's however you want to think about it. So it's 10 moles of water produced. All right? There's always multiple ways to solve a problem, always multiple ways to solve a problem. This is the way that makes the most logical sense to me. In your books, you may have a slightly different way of attacking it, and if that makes sense to you, that's great. I'm just showing you my way of thinking about it. My way is not always the best way. It's just the best way for me, okay? So what we've done is we've learned from our peanut butter and jelly what the concept of a limiting reactant. Then we applied it to a very simple chemical reaction where I gave you the number of moles, and in order to figure out how much water is going to be produced, you have to figure out which one of these is going to run out first. And you cannot do it by looking at it. A lot of students will look at it and try to figure out what's going to happen. You can't. You have to calculate. Stop looking and calculate. So we say, well, if 10 moles of H2 is there, I'm going to need 5 moles of O2 to react with it. But I have 7, and that means that O2 has to be the excess reactant. H2 is going to run out first. We did the same exact thing here, and we again figured out H2 is going to run out first. So with the 10 moles that we have, it's going to run out first. It's going to produce 10 moles of water, and that's how much water is actually going to be produced. What I'd like to do, I have one more problem in this lesson. I'm going to erase all of this, give us room to solve our next problem, which was a little bit more rigorous. It's not that much harder, but it's a little more rigorous. We need the board space. So let's erase this, tackle our next problem, which will be a real limiting reactant problem. All right, here's our first real problem with limiting reactants. The following is a reaction of carbon dioxide with sodium hydroxide. The reaction, I'll write it down again, but it's CO2 as a gas plus 2 NaOH, that's sodium hydroxide, yields Na2CO3, which is sodium carbonate, plus H2O, which is water. So 4 different species in the chemical reaction. And part A says, if I have 1.850 moles of sodium hydroxide, NaOH, and 1.0 moles of carbon dioxide, which is the limiting reactant? So that's part A. There is a part B and a part C, but let's focus now on part A. What is the limiting reactant? We've already done that in the last problem. Now we have to do that here. And also, I'm going to show you 2 different ways to find the limiting reactant. One of them is what we just did for the water in the previous example. There's a slightly different flavor I'll show you. Also, it's very simple as well, but there's multiple paths to get to this answer. So the first thing we want to do is write down the reaction. So it's CO2 as a gas, and then 2 NaOH, sodium hydroxide, which is a solid, and this yields Na2CO3, which is a solid, and then H2O, which is a liquid. Now, we should spend just a second to make sure this is balanced, okay? So we have 1 carbon and we have 1 carbon, okay, that's good. 2 oxygens and 2 more oxygens for 4 oxygens. 3, 1 more is 4 oxygens, that's correct. 2 sodiums, that's correct. We've already done the oxygen, so there's 2 hydrogens and 2 hydrogens, that's correct. So this reaction is balanced. And so we're basically saying, I'm gonna write down what part A is. What we're reacting together is 1.850 moles of it's supposed to be a lowercase a, NaOH, sodium hydroxide. We're reacting with that 1.0 moles of CO2, and which are these 2 species. And we're asking each other, I'm asking you, which of these 2 is the limiting reactant? All right, so here's our strategy. There's a method 1, which we're going to do first, and then there's a method 2. I have not told you method 2 yet, but just trust me when I tell you it's not difficult. Method 1 is going to be basically exactly what we just did for the previous problem in water. What we're going to do is we're going to forget about this. We're going to start with this amount of sodium hydroxide and calculate how much carbon dioxide is needed to bond with it, and then from that we'll be able to determine the limiting reactant. So let's do that. We have down below. Let's do this. All right, let's say we have 1.850 moles of NaOH. That's sodium hydroxide. And if we want to figure out what is the limiting reactant, let's see how much carbon dioxide would be needed to fully react with this amount of sodium hydroxide. They react in a ratio of 2 moles of this to 1 mole of carbon dioxide. So 2 moles of NaOH on the bottom, so it cancels, reacts with 1 mole of CO2, right? Just like this. And the units we have left is carbon dioxide. So if you take 1.850 times 1 divided by 2, you get 0.9250 moles of CO2. Now this is enough to actually figure out which one of these 2 is the limiting reactant. What this is saying is that if I actually start with this many moles of sodium hydroxide, it's going to require just less than 1 mole, 0.9250 moles of carbon dioxide to fully react with that amount of the other reactant. However, this is how much is needed of the carbon dioxide, but I actually have more than that in my reaction vessel. So I'm not going to run out of carbon dioxide first because I actually have excess carbon dioxide. So what I'm going to write down is that CO2, this is the excess reactant. Why? Because I have excess to the amount I actually need to bond and react with this product. And that means that the sodium hydroxide must then be the limiting reactant. So this means that sodium hydroxide is the limiting reactant. All that means is that when you mix these 2 amounts in a vessel and try to react it according to this reaction, the sodium hydroxide will run out first. And I will have some leftover carbon dioxide that's unreacted because it only takes this much to react with this, but I actually have a little more there. I have a little more in the vessel. So this is actually enough to circle the answer. So I'm going to go ahead and circle the answer because the first part says, which is the limiting reactant. So I'm going to circle that sodium hydroxide is the limiting reactant because that is the answer to the question. But I also want to show you that there's more than one way to do this. So this is still method 1. We have not moved on to method 2 yet, but I'm going to show you that if you don't start with this reactant, if you start with the other one, you get to the same place. So what we're going to do is come down here, and we're going to start instead, just to check, we're going to check these results by saying 1.0 moles of CO2. According to this chemical reaction, if I really do mix this amounts together, if I start with this much, how many moles of sodium hydroxide will I actually need in order to pull off this reaction? Well, they react in the ratio of 1 CO2 to 2 moles of sodium hydroxide. So 1 mole of CO2 to 2 moles NaOH. And of course, the moles of CO2 cancel. So what this is basically telling us is that if I start out with 1 mole of carbon dioxide, how much sodium hydroxide is required to react with it? 1 times 2 is 2. So 2 moles of NaOH required. In fact, I'm going to write the word required here. Required to react with the other number that I had in there, okay? So what this is basically saying is that if I start with 1 mole of carbon dioxide, I must have 2 moles of sodium hydroxide, right? This is exactly what the reaction is. However, I'm actually starting out with less than 2 moles of sodium hydroxide. I am starting out with 1.85. That's less than the required amount I need. So therefore, because of this, then I'm basically getting to the same conclusion again, that the carbon dioxide is the excess reactant. So the CO2, just like before, is the excess reactant. And the NaOH, the sodium hydroxide, is the limiting reactant. And so that's a check mark because that matches what we have before. Now, how do you know this is the case? Well, if we start with the other reactant, the CO2, and we calculate how much sodium hydroxide we need to react with that, we get a number that's actually more. We need more sodium hydroxide than's actually there. That means that we're going to actually deplete the sodium hydroxide first, and that is why it's the limiting reactant. And so the CO2 must be in excess. It has to be, because if you're going to run out of the other thing first, then you must have the excess of the CO2. So that part 1 was just having us calculate and figure out which of the 2 reactants is the limiting reactant. And that's what we call method 1, right? Or I call method 1. So I guess I'll just go over here and say method 1, right? There's always more than one way to do something, right? So let's go over here and talk about method 2. Now, ultimately, I actually don't care which way you do it, method 1 or method 2, because they both have their advantages and disadvantages. It really boils down to what you're being asked in the problem. Sometimes the problem may ask you something about the reactants, and doing it this way is you kind of get the answer as part of that process. Sometimes the problem's asking you more about what's happening with the products, and then this way, number 2 way, is going to be, you'll be calculating as we go here. So sometimes you'll choose method 2 because you need to calculate things with the product. In method 2, what we're going to do is we're again going to be mixing this amount of NaOH and this amount of carbon dioxide together, same thing. What we need to do is figure out how much product is formed in both cases, right? So what we're going to do is we're going to assume that this much sodium hydroxide is reacted with plenty of carbon dioxide, excess carbon dioxide, and calculate how much product is forming. Now, there's the sodium carbonate as the product and the water as the product. In your reaction, you're going to have to determine which product is the most important product. I mean, the water is not going to be the focus of this reaction. The sodium carbonate will. But ultimately, to figure out which one is the limiting reactant, it isn't really going to matter which product you pick. Notice you form 1 mole of each of these products. So we're going to pick this one. It's not actually going to matter. Let's just calculate how much product we're going to form in each of these 2 cases. And I think you'll see very quickly what is happening here. And we'll be able to determine which is the limiting reactant. All right? So what we need to do is, what we say is that we're reacting 1.85 moles of sodium hydroxide. So 1.850 moles of sodium hydroxide, NaOH. All right? Now what we're going to do is ignore the other reactant. We're going to just basically pretend that the other reactant is an excess reactant and that this is the limiting reactant, so to speak. And we're going to calculate how much product we would actually form in this case, right? So we know that if we start with a certain amount of sodium hydroxide in moles, 2 moles of sodium hydroxide makes 1 mole of sodium carbonate. So we'll put that in here. 2 moles of sodium hydroxide form 1 mole of Na2CO3, like this. But the moles of sodium hydroxide cancel with the moles of sodium hydroxide. So what we're going to calculate here is how much product would form in this case if the other reactant, the carbon dioxide, is just in excess and I have tons of it to soak it all up and just convert all of this into product. So I'm going to take the 1.850, multiply by 1, and divide by 2, and what I'm going to get is 0.9250 moles of Na2CO3 produced. All right, produced. Now that's not really enough to figure out which is the limiting reactant. What we have to do is do the whole thing again. We calculate how much product is formed with this being the limiting reactant, and then we switch to this one and say, okay, let's pretend this one's the limiting reactant and see how much product is formed. Let's go ahead and do it, and I think you'll understand. 1.0 moles of CO2, right? Now, if this were the limiting reactant, reacted in excess of the other stuff, when we reacted 1 mole of CO2 to 1 mole of of the sodium carbonate, so we write down 1 mole of CO2 forms 1 mole of Na2CO3. Cancel, cancel. So what have we figured out here? We figured out, okay, if we assume the carbon dioxide is the limiting reactant and we have an excess amount of the other reactant available to react with it and convert all of this into product, there's ones everywhere. It's going to produce 1 mole. I guess I could put 1.0 mole, put 1.0 mole of Na2CO3 produced. All right, both of these cannot be true. In the first case, if I have 1.850 moles of the sodium hydroxide reactant, and I allow all of that reactant to be converted into product because we're pretending it's the limiting reactant. We don't know, but we're pretending it's a limiting reactant, and convert all of it to product, then we make 0.9250 moles of the sodium carbonate. But if we switch gears to the carbon dioxide and say, well, what if it is the limiting reactant and let all of the carbon dioxide be converted into product, then this should produce exactly 1.0 moles of the sodium carbonate. Which of these two is true? You have to pick the smaller number because the smaller number of the product produced means the reaction is going to stop sooner. And remember, the limiting reactant is whichever of those two reactants runs out first. So by using both of them separately to calculate theoretically how much product they would make in a vacuum, not literally in a vacuum, what I mean is isolated by itself, converting each reactant all the way to product, convert the other reactant all the way to product, and seeing that these two numbers are not the same, this one must be truth. Because what's going to happen is this is going to get converted to product, and there's going to be a little bit of extra carbon dioxide left over because it would have produced more product. So by looking at this, then you can see that because this number is smaller than this one, it produced less amount of product, then the sodium hydroxide was the limiting reactant. And the other one, the CO2, was the excess reactant. And I'm using the word reactant. A lot of times you'll see the word reagent. Reactant, reagent, basically the same thing. It just means input chemicals to the reaction. All right, we do have another couple of parts to this, but we have actually conquered the lion's share of the learning in this problem. So I want to stop for a second. I want to go back and review both of these methods, and then we're going to conquer part B and part C, which will go very, very fast because they're very easy to understand, okay? So we have this chemical reaction. 1 mole of CO2 reacts with 2 moles of sodium hydroxide to yield 1 mole of sodium carbonate and 1 mole of water. If I react or I mix 1.850 moles of the sodium hydroxide together with 1 moles of carbon dioxide together, which of these two will be the limiting reactant? There are two methods. The first method is to use this amount and see how much of the other reactant is needed to bond with it according to this reaction. So if you have this much reactant, it's going to take 0.9250 moles of carbon dioxide required, which is less carbon dioxide than I actually have. So I know the carbon dioxide has to be excess, and I know the sodium hydroxide has to be the limiting reactant. Now you can check this by doing the same calculation using the other reactant, CO2. Let's see, if we start with 1 mole of CO2, how much sodium hydroxide is required to bond with it fully, right? When we do that math, according to the mole ratio in the reaction, we calculate that 2.0 moles of sodium hydroxide is required. But we only have 1.850 moles, which is actually less. So that tells us right away the sodium hydroxide is the limiting reactant. It will be depleted first. The carbon dioxide is the excess reactant. So method number 1 involves looking at both of the input reactants and just using one to calculate how much of the other you need. And you could go backwards the other way and just compare and see what's going to run out first. That's method 1. Method 2 is to do 2 different calculations where we take one of the reactants and convert it completely into product. And then we take the other reactant and convert it completely to product. Now, when we do this, we're assuming implicitly that the sodium hydroxide is the limiting reactant. We have excess of the other, and we just do that in both ways and figure out how much theoretically could this amount theoretically produce. How much of this carbon dioxide could theoretically be produced with the sodium carbonate. And we find out that the fewest amount of moles of sodium carbonate is produced with this reactant. In other words, this one's going to run out first, producing this much. There's no way it can produce this much, because what's going to happen is I'm going to run out of this in real life before I deplete the carbon dioxide. So when you get the 2 answers, you just discard the bigger one. The smaller one means this one is the limiting reactant, the sodium hydroxide. The other has to be the excess reactant. A lot of talking, right? Part B. Now here's where we go with part B. Part B, how many moles of sodium carbonate will be produced? Now you see, there's a method 1 and a method 2 for finding the limiting reactant. Now you see why you might choose one over the other, because part D says how many moles of sodium carbonate will be produced. Well, if we go over to our original method number 1, we just figured out what's the limiting reactant. Once you figure out sodium hydroxide is the limiting reactant, and you know how much you started with, you would just go through the stoichiometry to calculate, starting with this much, how much product would you form, assuming an excess amount of carbon dioxide, which is what we have here. But we've already done that calculation in part 2. We started with this amount as a limiting reactant, and just to see what would happen, how much sodium carbonate will be made. And we already calculated it's 0.9250 moles. So for part B, how much will be actually made? 0.9250 moles of whoops, if I can write it down, sodium carbonate, Na2CO3. So I can just circle it because I've already done the math here. And this is a good example of why you might choose to do the calculation this way. If you know you're going to have to calculate the amount of product, maybe I'll just find the limiting reactant this way, and then I can write down the limiting reactant, and I've already calculated the amount of product that's going to form, and I just circle it for my next answer. All right, so we're done with that, 0.9250 moles of sodium carbonate. All right, part C, this is the last part. How many moles of excess reagent will be present after the reaction? How many moles of excess reagent? Remember, excess means how much is left unreacted after the reaction is finished. But we now know that if we mix this many moles of sodium hydroxide with this many moles of carbon dioxide, what's really going to happen is the sodium hydroxide will be completely depleted, right? And a portion of the carbon dioxide will also be depleted, but there'll be a little bit left over. How much will be left over? Well, we could do that math again. If we go back to method 1, assuming that we start with this as a limiting reactant, which is what it is, how many moles of carbon dioxide will it require to be bonded or to react with this amount of sodium hydroxide? Now that we know this is the limiting reactant, we calculated that this is going to be the amount of carbon dioxide consumed in this reaction in the case that this is the actual limiting reactant, okay? And so this amount of carbon dioxide, we have a little bit more than that. So for part C, how much excess reactant will be left behind, what we have to do is take the 1 mole of carbon dioxide, which was in the reaction vessel, and then we subtract off how much carbon dioxide was actually consumed, 0.9250. Right? And then take the 1 minus that, you get 0.0750 moles CO2. So basically, part B and part C were obtained in the course of doing this problem two different ways. If I didn't do the problem two different ways, then you would have to do that calculation. But effectively, all you're basically figuring out is if you want to know how much excess reactant is left, you know that the limiting reactant must be completely gone. And so then you just need to calculate how much of the other reactant was used. And so you start with that limiting reactant. In this case, we now know it's sodium hydroxide. How much carbon dioxide will react with it? It's in a 1 to 2 mole relationship. This is how much carbon dioxide will be used up in this reaction. This is how much we started with, minus this amount. That's all the math we did here. This is the amount in excess. I'll write in excess. And that is it. So this is a pretty long lesson. We started out by talking about what is a limiting reactant, talking about sandwiches and trying to make it something that you can burn in your mind. Then we talked about the water reaction, H2 and O2 giving water, because it's very easy to understand. The numbers are very, very simple. And then we did this problem where we expanded on it a little bit. Remember, two main ways to find the limiting reactant. One is to take the reactants, figure out how much of the other reactant is going to be required to react with it. From that, you can determine the limiting reactant. Or method two is to take your original reactants, calculate the product, and see which one is smaller. And that will yield the limiting reactant. Either is fine, depends on what you have for your problem. You can choose either path. And as I go forward, I'll probably choose different paths for different problems. But I had to show you at least once that you could do them both and get the same answer either way. So I'd like you to solve this problem yourself. In fact, I'd like you to solve it both ways yourself, and then follow me on to the next lesson. We'll continue solving problems involving the limiting reactant. Learn anything at mathandscience.com.